In this video, we will look at a problem that requires very sharp observation skills to solve. This is a very controversial code forces problem because these kind of problems are the hallmark of AdCoder, but this problem actually appeared in a code forces diff2 round at position D, and of course people were not happy about it. So let's see if you are able to solve this problem. So the description says that you are given an array and let us color all the green elements, all the even elements in green. So just so that you remember, even has two e's, and that's why I have labeled all the even elements. I have colored them in green. So 2, 4, 8 and 6, they are colored in green. And let us color all the odd elements in blue color. Then you can do a series of operations as many times as you want. You can do infinitely many operations on this array, and in one operation you can select any subarray and you can reverse it. But there is a criteria, and the constraint is that you can only reverse if the maxima and the minima of the subarray are of different colors. For example, you cannot reverse this. So if you take this subarray 4186, you can reverse this because the minima is 1, which is blue, and maxima is 8, which is green. But you cannot reverse this subarray because maxima and minima are the same. Similarly, if you pick this subarray 794, maxima is 9, which is blue, and minima is 4, which is green, so you can reverse it. So you can only reverse a subarray if the minimum element of this subarray and the maximum element of this subarray, they have different color. Only then you are allowed to do the reverse. So you can do the reverse as many times on this array as you want. The problem asks you to find, is it possible for you to sort the array after doing these operations any number of times? This is the entire problem statement, and take a minute to pause this video and think about how you would approach this problem, because once you see the solution, the solution idea sounds pretty trivial. Like I said in earlier videos, that hindsight is 2020, because in these kind of sharp observation skills problem, after knowing the solution, there is no going back. So it all comes down to whether you are able to go into the right direction of approaching this problem on your own. So it is possible that in the contest you might freeze and you might not even be able to start thinking in the correct direction. So let me show you how you could have approached it in a contest, even though I doubt I could have even solved it by myself during the contest. So in these kind of problems, which are very typical in AdCoder, what you should do is realize that whenever the problem is asking you to do an operation any number of times, either there would be a very trivial strategy, or the total number of operations would be very small. Or another case could be, if you are not able to make any progress, you start locally. That is, you start by analyzing some case locally and then see if you can generalize this to bigger subarrays, because right now it's very difficult to analyze when would you reverse this, is the reverse even possible, is the reverse even beneficial. So how do you start small? How do you start locally? So to start locally, let's consider all the subarrays of length 2, right? Because these are the minimum length subarrays that you can swap. So when can you swap that? If both of them are of the same color, of course you cannot swap, because one would be the minimum, one would be the maximum. So if you have adjacent elements, then if they are of different colors, you can definitely swap them. Now this seems like a very trivial observation, and it looks like that this won't really help us solve the problem. But in fact, if you have arrived at this conclusion, then you are already halfway there, like more than halfway there. Like you have already solved 80% of the problem. It is not yet clear how, but in the later slides I'll show you that if you could arrive at this conclusion by yourself, that let's start small, let's start locally. And in locally, you can see that if you have a blue element and a green element, then you can swap them, because one of them will be the minima, one will be the maxima, so swap is always allowed. And why is this so much powerful? Like swapping elements of two color is always allowed. But why is this powerful? It is powerful because with this information, now you can segregate all the blue elements together and all the green elements together. This means that if you consider this green element, right, this element 4, this can actually jump through this 9. It can, if you want this 4 to appear between 7 and 9, it can do so. If you want it to appear between 5, 4, 7 and 9, it can also do so. If you want it to appear between 2, 4, 5, 7, 9, that is also possible. So this means that any element, right, if you have a green element and then if you have a series of blue elements over here, then they are not acting as a barrier. This element can jump and then directly land over here. Or you can say that it can make a small jump, it goes here and then it goes here and then it goes here, goes here and goes here, and then finally it reaches here. But notice that it cannot jump past a green element. So for example, if you have this 2 and this is 4, and let's say both of them are colored in green, then they cannot be swapped, right? Because you cannot swap a subarray of length 2, because one will be the minima and one will be the maxima, but both of them are of the same color. But at least from here you can infer that elements can jump between the elements of the same color. So what can you do with this observation, this jump observation? At least you can segregate all the elements of the same color together. Why is this segregation possible? Because 5 can jump to stay on the right hand side of 7, then 7 is already here, 9 is already here, 1 can also jump to here. And if you do that, you can get this structure, like all the green elements here and all the blue elements here. So once again, this is very crucial part of the analysis. So let me recap. We are saying that if you have this structure, then it's possible for 5 to jump all the green elements and be with its sibling, which is this next blue element. It cannot jump this blue element yet, but this one can be close to this 9, and wherever this one is, 5 can live right next to it. So you can see that these jumps, they preserve their relative ordering, because you are jumping between elements of the same color, but you are not jumping between elements. So you are jumping between elements of the different color. So that's why even if you were to do this restructuring, you will notice that you will have 2, 4, 8 and 6. That's what you see over here. 2, 4, 8 and 6, and 7, 5, 7, 9, 1, 5. 7, 5, 7, 9, 1, 5. So then you have the blue elements over here. So their relative positioning is not changing by jumping, but if you need it, then you can segregate. Now, why is this observation helpful? Because notice that the operations are reversible. And what do I mean by reversible? That if you are allowed to swap, if you are allowed to reverse a subarray, and suppose this is the green element, this is the minima, this is the minima, and this is the blue element, this would be the maxima. So if you are allowed to reverse this subarray, then you can, whatever the reversal be, you can reverse it again, right? You can reverse it 2 times. So if the answer to the original problem is yes, that it is indeed possible to sort this array, then it should also be possible to sort this array where you have segregated all the elements on one side and segregated all the elements on the other side. Why? Because there is a one-to-one mapping between them. Like if you can reach from this subarray to this one, then you can also go back, right? So this means that now you have simplified the problem. That is, if we can sort this independently and this independently, and then we can come up with a strategy to maybe merge them, then we can then maybe we are on the right track to solving this problem. But suppose that these two you have sorted somehow, right? Or for now, let's assume that this green element is sorted by itself and blue elements are sorted by itself, because we said that relative ordering is not changing. So let's consider the easiest case when they are already sorted. So if they are already sorted amongst themselves, and they are already sorted amongst themselves, can you merge these to create a final sorted array? Yes, again you can utilize the power of jump. So we said that any element can cross all the blue elements and then jump to any position. So if you need the smallest element as 1, you keep it over here. But with 2 pointers, you can check which is the smallest element. It is actually this green element, and since the green elements are sorted, then green element will only have to jump over all the blue elements which it can, and it can land over here. Then the smallest element that you need is 3. That's fine. Then the smallest element you need is 4. So 4 can jump over everything. 4, now notice that 4 doesn't have to jump over 2 anymore, because 2 has already gone to its correct place. And the thing that is helping us is that everything is sorted in the green block, so nobody has to jump over a green element. So you can put a green element over here, then you can put a blue element, and then you can put a green element. So now you can say that if the blue elements are sorted and the green elements are also sorted, then it's possible to merge them. Why it's possible to merge them? Because the smallest element will appear first in the array, so it can jump to any position that you want in the sorted array, just like merge sort. And then the second element can jump, but when this second element is jumping, this will not block it. Why? Because it will never jump to the left side of it, because this is bigger than this. So what can we conclude from this? So we can only conclude that, okay, if we are lucky, that is, segregation is always possible, that we know of. So we'll first do the segregation, and we'll have all the blue elements in one place, and we'll have all the green elements in one place. And then we see that if all these elements are relatively sorted amongst their color, and all these elements are relatively sorted amongst these colors, then you can simply apply a merge sort strategy to merge them. Not that the problem actually asks you to merge, it just asks you to print whether it is possible or not. So to check that, you just have to check whether the blue elements are sorted, whether the green elements are sorted, and just print yes or no. But now, if the final array has to be sorted, right, then remember that we said that all the operations are actually reversible. So if the operations are reversible and the final array is sorted, it means that these blue elements, even if they are not sorted currently, they have to be sorted amongst themselves first. And same for these green elements, even if they are not sorted right now, you will have to sort them. That is a necessary as well as a sufficient condition. Why is that true? Because assume in the final array right now, suppose this was something like this. This was something like 3, 1, 5. This is not sorted. And this was something like 6, 2, 4. This is also not sorted. But if the final answer is yes, the array can be sorted, then it means that there is a configuration in which you have 1, 2, 3, 4, 5, 6. Now, if there is a configuration that exists, then we can reverse engineer this configuration from that. Why? Because let's label it 1, 3, 5, and 1, 3, and 5 are blue, right? So this is blue, blue, and blue, and 2, 4, 6 are green. So let's label it like so: 2, 4, and 6. And then we said that any element can jump. So if they can jump, it means that you can have this configuration. You can have this configuration of 1, 3, 5 from this sorted array, because you can reverse the operation. And then you can have the configuration of 2, 4, and 6. So what does this mean? This means that if sorting is possible, then sorting the individual colors should also be possible. That is necessary but also sufficient. So now we have isolated the problem to only figuring out how we will sort the individual colors, because once we have done that, then we can simply apply this merge sort strategy to do the final sorting. But how do you sort the individual colors, right? Because we know that elements can only jump between colors of different between different colors, right? Only different colors element can jump past each other. But notice that that was just one of the conditions, right? This was just sufficient. Like if you wanted 7 to jump to 2, we said that it is possible, but maybe it is also possible for elements of the same color. If this is green and this is also green, maybe it is possible to jump, maybe it's possible for this X to jump over here, because you could as well select a bigger subarray, right? We don't know yet. So this was just a sufficient condition that with subarrays of length 2, you can move around 2 elements of the different color. But what about elements of the same color? Because now we want to know what is your strategy to sort a single color, because that is a necessary as well as a sufficient condition. Now suppose you are focusing on this green color and you want to sort it. So you see that okay, 4 is sorted, because it is the minima. 4 and 6 are also sorted. Now you encounter 2. So when you encounter 2, you know that 2 should jump over this element and also jump over this element and also jump over this element and land over here. So now the question that we are asking is, can 2 jump over this 6? So if you do any operation of length 2 or even length greater than 2, but if you only include this green block, then it's not possible, because if you only include this green block, then the minima resides here, maxima resides here. So minima and maxima are not of different color. So one thing is for sure, at least one element from this block will be used. And again, I want to remind you that all the operations are reversible. So that's why solving the problem on this is equivalent to solving the problem on the original array. And this actually simplifies things. So that is why we are solving the problem on this isolated version. So of course, if you have 6 and if you have 2, then when you are doing the reversal, when you are doing any reversal of the subarray, either you don't include any of these elements and then you do a reversal over here. But if you do a reversal over here, then the relative position of these two elements does not change. And even if you do a reversal on the left hand side, the relative elements will not change, right? Then that means that when you are doing the reversal, and even if you, like, let's say do a reversal something like this, a big reversal like so, even in that case the relative position of 6 and 2 has not changed. This means that in order for 2 to jump over 6, the reversal must contain, if you want 6 and 2, if you want them to jump over, it must contain a blue element. Let's call it as Z. Okay, it must be a blue element, this Z. You have this 6, you have 2, they are living close by, and then there must be some element Z. At least this is one blue element. So there is a blue element Z. We don't know what this Z is. And if you use this Z as an anchor, then and if you reverse this subarray, then you can see that Z will land over here and you will have 6, sorry, you will have 2 and 6, and then you can 2 can land over, 2 can cross this Z, right? And then it can come back to its, like, you can do this reversal and then you can do the segregation again, because segregation to green and blue is always possible. But what can you say about this Z, right? So let's notice this, like if you have 6, you have 2, and you are using an anchor over here, this is an anchor, you absolutely need this blue element for the reversal to happen. But what are the properties of this Z? Now let's look at the number line. This is 2 and this is 6. Now this anchor Z, this at least one blue element that you have included, if it lies in this interval, suppose Z lies in this interval 2, 6, then the minima would be 2 and the maxima would be 6, right? And then the 2 and 6 have become the same color. But you might argue that there could be different Z that is outside this interval and that is acting as the minima. So sure, if there is a different z, let's consider that as the correct z. What I'm trying to say is that there should be at least one blue element outside this interval, because if all the blue elements, you can write this claim that if all blue elements, if all the blue elements are inside this interval, then the minima is 2 and the maxima is 6. So it's not possible. So if all the blue elements are strictly inside this interval, so it's not possible. So this means that there should be, you can write this down, that a necessary condition is that necessary condition is that there should be at least one anchor, and anchor is nothing but a blue element that is outside the interval 2, 6. Because if all the blue elements are inside the interval, then there is no anchor for you to do the swap. And then if there is no blue element, so if all the blue elements are inside this range 2, 6, then you know that the answer is no, because no matter what operation you do, you can never swap 2 and 6, because no element can act as an anchor over here. So now this is, you can say this is a necessary condition, and this is where your sharp observation skills will come into play. Now if I were to tell you that okay, there is at least one anchor on the blue side, that is first of all, what are the possible candidates for the anchor? So notice that we are only interested in any element that is smaller than the minimum element, or the bigger than the bigger element, right? So the anchor candidates for the anchor are what? Let's consider the minima of the blue element, and let's consider the maxima of the blue element. Now here you see that you have this 6, you have this 2 over here, and you want to swap them. You want 2 to jump over 6, but you don't want to change anything else. Everything should remain as it is, because if you can do that, if you can silently swap this without touching anything at all, then you can silently keep on swapping green elements, right? Because that is a necessary condition. And if you can show me that it is also sufficient, if you can show me a strategy for the swap to be done, then you are good, right? You should be able to sort the array. So now take a minute to pause this video and think of a strategy of how you could swap this 6 and this 6 and this 2 using this anchor. Let's suppose this is the minima. You can use this as an anchor because this is outside this interval 2, 6. How would you actually swap it? Because you will immediately run into a very big issue, and the issue is that this anchor, this cannot come here to help it. Why? Because anchors cannot jump past their blue elements, because blue elements cannot jump across a blue element. Similarly, if you try to be smart and said that okay, if the blue element is not coming to me, I can jump over all of these elements and go to this blue element to do the swap. That is also not possible, because you will have to jump over a green element, which we know is a bit difficult. I mean, that is exactly what we are trying to find out, like when is it possible to jump over a green element. But suppose there was some strategy to bring these elements closer, like if you could bring this 6, 2, and let's say this is your anchor. This is your anchor, meaning this z is outside the interval 2, 6. In that case, what is the minima of this? So the minima of this is, if z is over here, then the minima is z and the maxima is 6. But if z is over here, then the minima is 2 and the maxima is 6. In either case, the minima and maxima are of different color, because will either be the minima or the maxima. So if you can create this interval of length 3, so now you can see how it is naturally tying up. Previously we saw how things work on intervals of length 2. Now we are investigating how things work on interval of length 3. So interval of length 3, as long as you have an anchor is the one that lands outside this interval. As long as you have that anchor, you can actually swap this interval. So if you can swap it, it will become what? Z to 6. And you see, with this anchor, you just swap 2 comma 6, and then you can send this anchor back. All of this is fine, but all of this is only under the assumption that you can bring the anchor closer to 6 comma 2. But from this image, do you see a strategy to bring this one over here without violating any of the rules that we have discussed and without disturbing any of the elements position? So the answer is staring right at your screen, but in case you are not able to see it, the answer is this. You want one to jump over and come over here to help out this 6 and 2, right? So that they can create this 6 to 1, and then they can swap it, and then one can go back. Problem is that one cannot jump from 5 and 3. But remember the first rule that we said, that jumps of length 2 of different color are very powerful. This means that what is blocking you from jumping? It is actually this 3 and this 5. So can you not move this 3 and 5 out of the way? Yes, there is a smart way to do that. You can do that by taking this first element. So nobody is blocking this first element because there is no blue element to the left hand side. And we know that a blue element can jump past all the green elements. So why don't we put this 3? Why don't we jump this 3 to the end? Like we segregate all the 3 over here. This is the 3, and then nobody will stop 5 from jumping past all of these green elements. So let's take 5 and place it over here. And then you have this 4, you have this 6, and you have this 2. And now nobody can stop this 1 from jumping and coming over to help this element 2, right? So 1 can jump over this entire thing and come over here to help out, and the remaining elements, their ordering will not change, right? So it will become 8, it will become 10, and then it will become 7, it will become 9. And now you see that relative ordering of nothing has changed, but you have brought the anchor closer to you, so you are not disturbing the relative ordering of any position, and you are able to swap out these two elements of the same color. So you have just found out a strategy to always swap elements of the same color as long as there is at least one anchor Z which is outside the interval that you are dealing with. So once you do this swap, your result would be something like this. Your result would be, suppose you do this swap, then your result would be 1 will come over here after this swap. This is 1, and then this is 2, this is 6, and then you have to place everything back in their original order. So it should look like that you just silently swapped 2 comma 6. And how can you do that? Same strategy. You send the anchor back to where it came from, and then you send these elements back to where it came from, and the final result would look like something like this. 3 5 sorry, the final result would look like this. You will have 4 2 6 8 10, and then you'll send this anchor back first. So anchor will exist over here 1 7 9, and then you send this 5 back, and you know that 5 will have no problem jumping over all of these elements and landing here, and then you send this 3 back. So after you have sent all the elements back, look at the situation looks like that you did not touch any blue elements, you did not touch any green elements, and you silently swapped 2 green elements. And you know that it was necessary for an anchor to exist, because if an anchor does not exist, then these 2 elements can never be swapped, this 6 comma 2, and the array can never be sorted. But if the anchor did exist, then you saw a strategy where you could silently swap them. So this means that swapping between different colors was always allowed. Now you have a strategy to also swap between elements of the same color. So how can you use that information to sort the array? Now you can use the technique of bubble sort. So previously we saw the merge sort strategy. Now you can use the technique of bubble sort. So what do you do in bubble sort? In bubble sort, you can see that this element 2, it needs to land over here. So you use this anchor and you swap this 2 and 6. So now it is 2 comma 6. And now you check this 4 and 2. This element 2 needs to land over here. So you do this 2, 4, 6. And this way, for each element, you can keep on swapping, and then it will land in its correct position. So just like you are checking if this element is inverted with its left neighbor. So this inversion and bubble sort, they are related. So this means that if these two elements, like if you want to sort the green elements, you can simply go from left to right, and as long as you are seeing increasing elements, you are good. As long as you are seeing increasing element, you are good. But as soon as you see a smaller element, this means that this smaller element has to jump from here till here till here, and then keep on landing in its correct position. So you can do that by looking for its anchor on the blue side. But if its anchor does not exist, you know that the answer to this problem is no, then the answer to this original problem is also no. So now you see that this problem, right? This actually required a lot of observation skills, and that's why people were not happy about it, because it appeared as a code forces diff to D. But anyway, let's look at the algorithm once again. So if you want to swap 8 and 4, you can use the anchor as either this 1, or you can use the anchor as 13, or even 11 works, but best candidates are the minimum element and the maximum element. So you jump this 13 over here by isolating these elements to the left hand side, and then you use that anchor to swap, and then you send everything back. So anchors are very powerful. They can help you to swap two elements of the same color, and then everything goes back in its normal place. And in that manner, you can sort all the green elements, you can sort all the blue elements, and using a merge sort strategy that we just discussed, you can combine them to produce this final result. This means that to solve the original problem, you don't actually have to implement this merge sort, inversion, bubble sort strategy, and then all of this strategy to bring the anchor around, send it back, because the answer was idea was just to print yes or no, right? So how do you do this? You find out all the green elements, and you find out all the blue elements, and you find out the minimum element in the blue section, which will be the candidate for anchor, and the maximum element in the blue section, which will be the candidate for the anchor. And then you iterate through all the odd elements from left to right, all the green elements from left to right, and as soon as you see an element that is smaller than its left neighbor, because you are processing from left to right, you keep on swapping. And you don't really have to swap, you just have to check for the existence of the anchor, because if the anchor exists, then you can just assume that this element is will be sent to its correct place, and whatever the maxima that you have seen so far, that will be the maxima, right? So the next comparison that you will do for 8, this you will do for this one 6, 8, and then this way you will be able to sort all the green elements, and then you can repeat the same thing for the blue element. And yeah, you can do this for green, and then you can repeat for blue, and all you have to check is the existence of anchors, because if they don't exist, we know that that was a necessary condition, right? But the sufficient condition for length 3, that was not necessary that you had to create an anchor and then create a length 3, but we just created it so that we don't touch a lot of elements. Not that that was a necessity in this problem, but in these kind of problems, that is the usual strategy to go with. Like you first start locally, like you start investigating cases with length is equal to 2, and then you try length is equal to 3 while doing the minimum number of disruptions, because everything is reversible and you are allowed to do infinite number of operations. So AtCoder has a lot of these kind of problems. Maybe you can try those. But yeah, I looked at the comment sections on Code Forces. Not a lot of people were happy about this problem appearing in a Code Forces diff to D round, diff to D position. So that's why this, I would say, it's a bit controversial, because it's a lot of far-fetched thinking skills, right? Nothing, no data structures, no algorithm, pure observations, pure skills. But how do you improve these skills? Just like the ideas that we discussed, right? To improve on this, you have to solve more of these kind of problems where you do something, right? Here we started with something like, okay, we have to start with length 2, and then make some observation and then follow up on it, because there is no playbook to solve these kind of problems. The more you solve, the better you become. So what do you think? Is this problem a good problem, or is this still a controversial problem, and a very hard problem, or very easy, or a very weird problem? Whatever you think, do let me know in the comment sections. Thank you.